Hello. Hello. Today we're going to be looking at the concept of equilibrium. And to get us started with equilibrium, we need to revisit a concept of rate of reaction. We've talked about factors that affect rate of reaction, and we haven't really talked about concentrations as a reaction takes place. So let's say that we have a real simple reaction where substance A is converted to substance B. Okay? And initially, before the reaction even takes place, the only substance you're going to have is substance A. So if we graph over here concentration of substance A, the amount of substance A we have, substance A is going to be up fairly high on the graph. It's going to be a certain amount, whatever concentration we're starting with. Substance B, on the other hand, and let's use orange for substance B. Substance B is going to be 0. We're going to have no product initially. And on the x-axis, and I forgot to label the x-axis, we have time. So initially, at time equals 0, we have no substance B product, and we have some substance A. Now, let's just pay attention to substance A. As time goes along, substance A is going to start decreasing, the amount of substance A. It's going to be reacting. And as time goes along, the rate of substance A's decrease is going to decrease. In other words, it's going to slow down how much substance A is disappearing over time. And eventually, we're going to reach an asymptote. We're going to reach a certain amount of substance A that we are not going to go less than. In other words, we're not going to run out of substance A. Not all of substance A is going to become substance B. As time goes along, substance B is going to increase. And so as time goes along, we're going to increase the amount of substance B, and it's going to increase, but the rate of increase is going to decrease over time. In other words, it's going to slow down how much substance B is being produced. And eventually, we're going to reach a point where we have the maximum amount of substance B that can be produced. So we're going to have some substance A and substance B present after this reaction takes place. Now, this point where we've reached the maximum amount of substance B produced and the minimum amount of substance A disappearing is called equilibrium. So at this point right here we have equilibrium. It's the point where the amount of substance A stays constant and the amount of substance B stays constant. And the change in concentration remains constant. In other words, we don't lose any more substance A and we don't gain any more substance B. That is equilibrium. The rate of change is 0. Notice the slope here on our graph is 0 for B. So we're not gaining any more substance B. The slope of substance A is 0. We're not losing any more substance A. This is what we call equilibrium. And what happens at equilibrium is that we don't just have B staying constant and A staying constant. We actually have substance A still becoming substance B, but B is also returning and becoming substance A. And so we use a double arrow to represent this idea of equilibrium, where A is becoming B and B is going back and becoming A. And so it's not just called equilibrium because there actually is change still going on. We kind of have a circle of A becoming B and B becoming A. It's called a dynamic equilibrium. Dynamic. And dynamic means movement. So if we have dynamic equilibrium, that means that we don't just have the substances sitting there doing nothing. We actually have changes occurring, but substance A is becoming B at the same rate that substance B, our product, is going back and becoming substance A. And this concept of dynamic equilibrium is a very important one in chemistry, and it's the point at which the rate of change of substance A equals the rate of change of substance B becoming A. The forward reaction rate equals the reverse reaction rate. So we can say rate forward, and I'll use an F, equals rate reverse, the backwards reaction. And this, right here, is our definition of a dynamic equilibrium, the point at which the rate of change of reactant equals the rate of change of product. The rate of the forward reaction equals the rate of the reverse reaction. So let's look at a situation that's slightly more complicated than this one. So I'm going to go ahead and get rid of this graph, And let's look at a slightly more difficult situation. Let's look at the situation where we have N2O4 dinitrogen tetroxide, and it sets up an equilibrium, which means it produces product NO2. But notice there's 2 nitrogens, so we need to balance this. 2 nitrogens and 4 oxygens, and 2 times 2 is 4 oxygens. And N2O4 is a gas, and NO2 is a gas. So we have a reactant becoming 1 mole of a reactant becoming 2 moles of a product. And so this is going to change what our graph is going to look like slightly. So on my graph, I'm going to use blue for my product, and on the graph, I'm going to use purple for the reactant. So let's look at what a graph of this reaction would look like. Okay? Again, we're going to put concentration on the y-axis, and we're going to put time on the x-axis. So let's think about what's going to happen just to the reactant over time. The reactant is going to decrease over time because it's going to be reacting. So we're going to start off with a certain amount of reactant, and then that reactant is going to decrease over time until it reaches equilibrium, where the rate no longer changes, where the concentration no longer changes. The concentration no longer changes. Now here's what's a little tricky about this one. For every 1 mole of N2O4 that I lose, I'm going to make 2 moles of NO2. So initially, at the beginning of a reaction, we have no product. And for every little decrease of 1 mole of N2O4, I'm going to gain 2 moles of NO2. So we're going to end up with a sharper curve of NO2. It's going to be steeper. It's going to be twice as steep at every point until we reach equilibrium. So for every mole we decrease of N2O4, we're going to gain 2 moles of NO2. So we have a steeper, sharper turn here, which means that there is a stronger, a steeper curve for NO2's production than there is for N2O4's reduction. And so this means that there must be a relationship that corresponds to this coefficient of 2 and N2O4's coefficient of 1. And so what is that relationship? And since they become a constant over here at equilibrium, there must be some constant that these final concentrations are equal to. So let's look at what the equilibrium constant is, what the relationship is between our equilibrium concentration of product, the blue line, and equilibrium concentration of reactant, the purple line. It turns out that the relationship, this idea of a constant, which we're going to give the symbol KEQ, which means equilibrium constant, is equal to the concentration of our products raised to the power of their exponent, which in this case is 2, but we'll just use x for the exponent here. And this exponent is just the coefficient, so coefficient of the products, divided by the concentration, and these brackets mean concentration, of the reactants raised to their exponent, which I'll give the symbol y. And that's just the coefficient of the reactants exponents. So in this particular reaction, 2 would be the exponent for the products, and 1 would be the exponent for the reactant. And so this equilibrium constant, which is called the equilibrium constant, is always equal to the products raised to the power of the coefficient divided by the reactants raised to the power of their coefficients. So for this particular reaction, the equilibrium constant is equal to the concentration of our products, which is NO2, so the concentration of NO2 raised to its coefficient power, 2, divided by the concentration of our reactants, which is N2O4, raised to its coefficient, which in this case is 1. And of course, with exponents, you don't have to write a 1, but I'm going to write the 1 just to emphasize that the coefficient was 1. So this is called an equilibrium expression. An equilibrium expression is simply the equilibrium constant equal to the products raised to its exponents divided by the reactants raised to their exponent. And this is the way we can solve for equilibrium concentrations. The amount of product we'll make in a reaction and the amount of reactant we'll have left in a reaction. And K is a constant for a particular reaction. And so with some examples, we'll see how this is important. But let's put this equilibrium constant in more generic terms and see what happens if there's more than one reactant or more than one product. So let's erase the screen and see what happens. So let's say that I have a reaction where we have substance A, oops, that's not an A, substance A, and its coefficient is a lowercase a, and this substance is a gas. And it reacts with substance B, and it has a coefficient of lowercase b, and it's a gas. And it produces substance C, and its coefficient is lowercase c, and it's a gas. And it also produces substance D with a coefficient of lowercase d, and it's a gas. What would the equilibrium expression look like for this? So we said the equilibrium expression, or the equilibrium constant, is equal to the products raised to their exponent divided by the concentration of the reactants raised to their exponent. Well, if there's more than one, then we can't just put one product and one reactant. We've got to put all the products and all the reactants. So the way that this works is it's the product of the concentration of each of our products. So we're going to multiply the concentration of C raised to its exponent, lowercase c, times the concentration of D raised to its exponent, lowercase d, divided by the reactants. So the concentration of substance A raised to its exponent times the concentration of substance B raised to its exponent, the coefficient of its, the exponent of its coefficient. And so here becomes a very generic form of the equilibrium expression. Substance A plus substance B producing substance C plus substance D. The reactants are always in the denominator and the products are always in the numerator. And we always multiply our products and multiply the concentrations of our reactants. And so let's look at a real problem and see how this works with real numbers. So we're going to look at a reaction that we've already seen, which is the N2O4 breaking apart into two NO2 molecules. And both of these are gas. So let's look at the situation. In a particular reaction, dinitrogen tetroxide decomposes into nitrogen dioxide. When the reaction reaches equilibrium, the concentration of dinitrogen tetroxide is 1.2 molar, and the concentration of nitrogen dioxide is 4.5 molar. What is the value of the equilibrium constant, KEQ? So we're going to write our equilibrium expression. And remember, equilibrium expressions equal the products raised to the power of their coefficient divided by the reactants raised to the power of their coefficient. So we're going to put brackets, meaning concentration of NO2 raised to its coefficient divided by the concentration of our reactants raised to its coefficient, which in this case is 1. And I'm not going to write a 1 this time because it's understood that there's a 1 there. And so here's our equilibrium expression for this reaction. We have our products and our reactants. And so now we're just going to substitute because we're trying to solve for KEQ. So we're going to plug into this equation the concentration of NO2 because brackets mean concentration in molarity. So NO2's concentration is 4.5 molar. So that's what I'm going to plug in to the numerator, 4.5 molar. And we're going to square it because the concentration of NO2 is squared. And then we divide this by the concentration of N2O4, which is 1.2 molar. So we put that in the denominator, 1.2 molar. Now notice that I'm not putting units here, and all through the semester and year I've been saying units, 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 units. It turns out for KEQ we don't use any units. And there's a reason for that. It's because the units change all the time for KEQ. so they just drop them off. So no units for KEQ. So this is our substitution to solve for KEQ, and now it's just a matter of math. So we're going to take 4.5 and square it and divide by 1.2, and when you do that, you will get a value on your calculator of 16.875. And notice I'm not putting any unit because K values, equilibrium constants, do not have units. The other thing is we need to round for significant figures, and since there's only 2 significant figures in each of our numbers we're using to calculate this equilibrium constant, we only put 2 significant digits in our answer. So we're going to round the 6 here to a 7 because the 8 rounds it up, and our final KEQ value is 17. And so that's our equilibrium constant. And what this means is by being greater than 1, this means that we make more product than reactant. The numerator is greater than the denominator. And remember, the numerator is product. So by having a value of K greater than 1, that means that we have more product. If KEQ was less than 1, that would mean our numerator was less than our denominator. And that's how we would get a KEQ less than 1. So one thing that the equilibrium constant tells us is that when KEQ is greater than 1, we're going to make a lot of product. And we use the term product favored. We're going to make more product. Whenever KEQ is less than 1, then we're going to say that it's reactant favored. In other words, not much reactant is going to produce product. We're going to keep a lot of reactant present. It's not going to make a lot of product. So this is an important concept here, an important interpretation of the equilibrium constant. When KEQ is greater than 1, we make more product, and when KEQ is less than 1, we make more reactant. And so you'll see in this particular case, KEQ is greater than 1, and you'll also notice that we had more product, 4.5 molar versus 1.2 molar. So important interpretation of the equilibrium constant. So this is one, we've done one problem now with the equilibrium constant. In the next video, we'll look at more problems with the equilibrium constant and also more interpretations of the equilibrium constant.